All right, happy Thursday, everyone. I hope you're all enjoying this gorgeous weather. Kind of hot. My classroom hit 80 degrees today at the high school. It was rough. Except I have a rule that if they're wearing a hoodie, they're not allowed to complain. A lot of these kids still wear hoodies even if it's 80 degrees in the classroom. But I say, nope, wearing a hoodie, you're not allowed to complain about the heat. So today we're going to work on or talk about binomial probabilities. So this section is probably one of the sections that gives students the most trouble historically. So hopefully if you have questions, ask them. Most of the time people go through the lesson and are like, yeah, that makes sense. That's pretty
It's
easy.
frozen.
You get to the homework and that's when the struggle is. So I'm here to help if you need it. But we're going to go through binomial probability distribution. I actually use this quite a bit. I used this type of math to prove to a student that I could tell that they were cheating because they said that they happened to guess on 37 multiple choice questions and got them all right. And they don't understand why I thought they were cheating because they just guessed on them all. So I calculated the probability that they would get them all right if they guessed on every single one of them. And it was small enough that they were like, yeah, you're right. I cheated. So not that that's where you're going to use it. Oh, I'm frozen.
You were
Y-
frozen.
Yeah, you
Uh,
just came back in, but
Oh,
we
okay.
missed the whole first part.
Oh, okay. We're going to do binomial probability distribution. It is tends to be the thing that people struggle with the most over the whole term. So make sure that you let me know if you have trouble after the class. Most of the time people get through the class and they're like, "Oh yeah, this is doesn't seem too difficult." But then when they go to do the homework, it's everyone is confused and everything. So make sure you're asking me questions because I don't know why this particular topic is where people struggle. I don't, I break it down as much as I can, and I'm not sure where the sticking point is. So hopefully you'll grasp it and maybe it won't be the sticking point this term. But I use this math a lot and hopefully it becomes something interesting and useful for you. So the first thing we're going to do is we're going to determine whether something is a binomial probability distribution or binomial experiment. We're going to look at the characteristics of a binomial experiment and see if it is or isn't. We'll see things missing. You'll see. Then we're going to compute some probabilities and we're going to compute the mean and the standard deviation of a binomial random variable. And then the graphing takes all of 30 seconds. So that is today. It'll be slightly longer than Tuesday, but it's really not a super long topic unless there's questions. So then you'll get to go out and enjoy this beautiful weather. So let's get going. Okay. So here are the things you need for something to be a binomial experiment. So um, you have to have a fixed number of trials. So I would say like I collected a sample of 30 students or I did whatever you do, you have to repeat it a fixed number of times. You have to have an exact number of trials you're going to do. And each of the trials needs to be independent. So like for example, if I was guessing on every single multiple choice question without even reading the question and just guessing on all of them, I'm going to have if it's there's let's say there's four choices, I'm going to have a 25% probability every single time because each one is going to be independent if I'm completely guessing and not reading the questions at all. So all 37 multiple choice questions, there's 37 fixed number of trials. Then they're all independent because each one's its own question and it's 25% chance of getting it. Number three, we need to have two mutually exclusive outcomes, success or failure. So with a multiple choice question with four answers, I have a 25% of success, 75% failure. There's two different things. Yes, there's four answers, but if only one is a success, then I have one success and three failures. So there's two different possibilities, a success or a failure. The probability needs to be fixed for each trial. So in the multiple choice question example, there's four answers and there's only one correct choice. I'm stuck at 25% chance of getting it correct every single time. So that's a fixed success. So these are the four things you need before before performing any kind of math with the binomial probability stuff. So these are the four things that you'll need to check. All right. So these are the variables you're going to see, or the symbols you're going to see. The lowercase n, this is how many trials you completed. So once again, 37 multiple choice questions. The n would be 37 because that's how many trials I have. P is the probability of success, whereas 1 minus p is going to be the probability of failure. X is going to be the number of successes. It's supposed to be a capital X, but frequently we're lazy and we don't hit the shift key and we use a lowercase. It doesn't even matter. It really doesn't even matter. But X is the number of successes. So if I'm trying to find out the probability of getting 37 correct answers with a 25% probability, the 37 correct would be my X and 37 would be my trials. Or maybe I want to know the probability of getting 15 correct. 15 would be my X and 37 would be my independent trials. All right, I'm going to go through some examples and we're going to talk about whether or not they're binomial. So let's take a look. And this one is going to be a binomial. So a player rolls a pair, a pair of fair dice 10 times. The number X of sevens rolled is recorded. So I have 10 times I rolled it. That's my fixed. This is my fixed number of trials. So fixed number of trials, it is a probability, the probability of rolling a seven is fixed. It's got to be the same no matter what, the probability of rolling a seven. Was that, I'm trying to remember, I think there's 6 different ways to roll a seven. I don't remember. We did that in week like 4 or something, and I don't remember what it was. But so there's a um, fixed number of ways that I can roll a seven. So that probability is fixed. And I could have a success or failure. I could either roll a seven or I didn't roll a seven. So that one is a binomial experiment. All right, so this one right here, there was supposed to be animation that made the answer pop up, but it's not happening. So we're just calling it good. See, the 11 largest airlines had an on-time percentage of 84.7 in November 2001. The Trying to look at the reasons for delays, the official randomly selects flights until she finds 10 that are not on time. The number of flights that needs to be selected is recorded. So our probability is fixed. Our successes and failures, what those are, that's fixed. But what's not fixed is the number of trials, because they're going to keep selecting flights until they get 10 that are not on time. They could end up selecting 50, 60 flights before they get 10 that are not on time. So therefore, this is not a binomial experiment because it's not a fixed number of trials. Make sense? Okay. So in this one, once again, ignore the red until I'm done. So in a class of 30 students, 55% are female. The instructor randomly selects 4 students. The number X of females selected is recorded. All right. So we have a fixed number of trials. There's 4 students, and looks like it has a fixed probability, and it does have a fixed probability, but the trials are not independent because as soon as I pull one student out of the class, well, for one thing, the probability changes because now I only have 29 students. So pulling one out is going to affect whether or not I pull out a female next time. So if I pulled out a female the first time, now I have less than 55% that are female left in the class because I already removed one from that population. So that one's going to affect the probability of the next one. These are not independent trials. Now,
So
if
if it
I
was
was
like
going to go
there
ahead.
were like there are separate classes that you were like each class was separate,
Yeah.
that become an independent.
Yes. Or if I put one of them back before drawing again. So maybe I took a student randomly out of the class, then I put that student back in. Now I'm going to randomly choose another student and then I'm going to put them back in. That would be fixed. So separate classes or if I put them back in. Good question. Does that make sense? Okay. All right. So we're going to construct a probability distribution for this right here. Um, I'm going to construct a really fun tree diagram, and I'm never going to ask you to make one, but it's going to kind of show you all the possible ways that things can happen, like for 4 trials. So 7% of the people in the United States have type O negative blood. So a simple random sample of size 4 is obtained, and the number of people X with the blood type O negative is recorded. So I'm going to show you what can happen with each trial because we took a size 4 sample. So let's take a look. So my first trial, I picked one person. In that one person either is a success, they either have type O blood or they don't have type O blood. So then my second trial. So now I either have a success and a success, or a success and a failure, or that I have a success or a failure and a success, or a failure and a failure. So each time I have a new trial, it's going to get bigger and bigger because my first trial could be success, and then my second one fail, and then my third one, I could have, I could have had success, fail, fail, or I could have had success, fail, success, 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 success. So as you move forward, there's more and more possibilities. What's really important here is at the end, there's one way that I could get 4 successes. There's one way that I could have all 4 of them be type O blood. One possibility. There is one, two, three, 4 different ways that I could have 3 successes. Okay, I see that. They're just not lining up, so it really confused me. But there's 4 different ways that I could have 3 successes. So 2 successes. There's 1, 2, 3, 4, 5, 6 different ways that I could have 2 successes. So this would be a whole lot of math to be doing this on our own without some special way to do it. I'm going to show you how we would calculate it, and it's going to make sense because we've done this before, how I would calculate each probability in a minute. See, there is 1, 2, 3, 4 different ways that I could have 1 success, and there's one way that I could have 0 successes. So all of this together is going to take a lot of math to get us where we need to go. I'm going to show you what this looks like on the next screen. All right. So I'm going to calculate these probabilities, and I'm not going to get all the way through all of them because it is just a lot. But for example, 0 successes is pretty easy because we're doing and probabilities. So a success, actually the 0 is a failure for the first trial, a failure for the second trial, a failure for the third trial, and a failure for the fourth trial. So remember, when we're doing and probabilities, we multiply all those probabilities together. This should be familiar from Unit 5. So I put 0.93, which is the possibility of failure, multiplied them all out, and this is my probability for 4 failures. So you'll recall that there were 4 different ways to get 3 failures. We had 4 different ways to get only 1 success. So therefore, I have 4 ways to get 3 failures, 1 success. So I take the 3 failures, so 0.93 to the third power times the 1 success. And there's 4 different ways to do that. So I multiply it by 4, and I get 0.22522. So once again, two successes. There were 6 different ways. So I have 2 failures and 2 successes. 0.02543. So you can see this is a lot of work because first you have to figure out how many successes and failures we can have, how many different ways that can happen, and then you have to do all this math. Thank goodness we have another way to do this. So I'm not going to make you do this. I just wanted to show you the math that would get us there, but we have a fun calculator function that'll do all of it for you. I hope you guys like the fun calculator functions because I love them. So here we go. You do not have to do this math. I'm just going to write no there. You are not going to do this math. Your calculator will do this anyway. This is um, giving us a different way. We used to use something called combinatorics, combinations and permutations to do these, but now our calculator can do something with called binom. So this function right here is what we're going to use. So what we use is the way this function works is it's binom PDF. This is my number of trials. This is the probability of success. And this right here is the number of successes. So if I wanted to know the probability of getting exactly one success, then I can use this, or exactly 3 successes, or whatever, we can use this function. This right here, when it's PDF, it means we're looking for an exact number of successes. We're going to have a different function if we want a range, but when we're using PDF, it's the exact number of successes. I'll give you a moment to label yours, and then we'll move on. I'm just going to get a drink of water. All right, moving on. Okay, so these are all the math symbols. This is a good page to like keep on hand. I'm not going to go through them, but this is a really good kind of just reference page for you because you will see things like less than. I'm kind of surprised that at least isn't here. So greater than or equal to, this one would be, oh, it does say at least. It does say at least because at least seems to be the ones that throws people off. But here's all just your math symbols for your greater than, less than, and all that. Okay, I'll show you exactly how to do this. So according to Experian Automotive, 35% of all car-owning households have 3 or more cars. In a random sample of 20 car-owning households, what's the probability exactly 5 have 3 or more cars? All right, so we can tell this is a binomial experiment because we have a fixed number of trials. There's 20 right here. There is a fixed probability of success, 35% chance of success. So that probability is fixed. We can assume that these are all independent because if I just took 20 car owning households out of like the whole US, I'm not likely to get 20 that are going to affect each other in any way. So that is mutually exclusive. They're independent. And then I have, this is number of successes that I'm looking for. So here's how we're going to do this. So I'm going to use binom. I'm going to show you how to do this in your calculator just a second. PDF. My number of trials is 20. My number or my probability of success is 0.35. And then the number of successes I'm looking for is exactly 5. So I'll let you write this down and then I'll show you on the calculator how to get there. All right, I'm going to pop over to the calculator. Here's my lovely fancy schmancy. Okay. The way that we get to this screen, we're finally hitting something other than stat. So you're going to hit the second button, which is this blue button up in the corner here, and then the button that says VARs. You should have this screen. So second, VARs. I'm going to scroll down because the binom PDF is A. We want binom PDF, not CDF. We want PDF. Then I'm going to go in there. Yours may not look like this. Mine looks like this, so it actually asks me for trials. If yours doesn't look like this, you're going to enter it in like this. If yours doesn't have that screen. If it does have this screen, it's pretty simple. We have 20 car owning households. The probability is 0.35. The X value, which is the number of successes, we want 5 successes. So 20 trials, 0.35 is my probability, and I'm looking for 5 successes. And I'm just going to hit paste, and it's going to paste it right there. And then hit enter. Let's see. Yes. Yay, Gwen, you did it. Okay, so I'm just going to round it to approximately 0.1272, or I'm going to say 12.72%. I don't care how you answer it. My open math does care how you answer it, so just pay attention to what they're asking for. Um, so there's about a 12.72% of getting exactly 5 people that own 3 or more cars in that sample of 20 car owning households. Questions? All right, let's move on. We're going to do and step it up one little bit. Oh, see, it does the same thing. All right. Okay, so now we're going to look at this probability that less than 4 have 3 or more cars. So we have a different function that we use for less than or equal to. So we do not have a function for greater than, but we have a function for less than or equal to. So the last one was binom PDF. We're going to use binom CDF. This C right here stands for cumulative. That's what the C stands for. And we use it when we're doing less than or equal to. So I'm looking for the probability that my X is less than or equal to, oh, it's less than 4. It's less than 4. I didn't realize it didn't say equal to. So the function that we have does less than or equal to. So we would look for the probability that X is less than or equal to 3, because 4 is not part of our solution, because we want less than 4 cars. 4 is not part of the solution, so do less than or equal to 3. This is what it's going to look like. 20 is my sample size. 0.35 is my probability, and then I'm going to put a 3 here because I'm looking for less than or equal to 3. So whenever you're looking for a range of values, you use the cumulative function for binom CDF. Whenever you're looking for an exact value, we use PDF. I think of PDF being precise, even though that's not what it stands for. It stands for probability, but I think of binom PDF is precise because we're looking for an exact number. Binom CDF is cumulative because we're looking for a range of numbers. If that helps you, great. If not, then just throw it away. So let's take a look at my calculator. So I'm going to do second vars. Scroll down to letter B. We want binom. Look at you being ahead of the game. Binom PDF. Once again, the number of trials is 20. Probability 0.35. My X value, we're looking for 3 or fewer. I'll give you a second to see what I have there. If you don't have this screen, it's going to look like this. You're going to type it in just like this. I'm going to hit enter. That's exactly what you got, Gwen. Good job. So that answer is approximately 0.0444, I guess. So there's about, so about a 4.44% chance that you would have, that a randomly selected person would have less than 4, or sorry, that you'd have less than 4 out of 20 that would have 3 or more cars. Questions before I confuse you even more? Not, I'm just kidding. Questions? All right. let's move on to at least. Okay. So this one now we're looking at least. You may recall back in chapter 5, I said every single time you see the word at least, you are going to use the complement rule. And I meant it. Every single time you see the word at least, you will use the complement rule. Every time. So let me kind of show you what's going on here because our cumulative function works with less than or equal to. So I'm going to do, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, dot, dot, dot. So what I'm looking for is the probability someone has at least three or more, or that four people, sorry, at least four people, I don't know where my brain is, at least four people have three or more cars. So I'm looking for the probability that any of this is happening, that it's four or more. That's what I'm looking for. I don't have a function for that. But what I do have a function for is this right here. So I can find this probability and then just subtract it from 1. So it's going to look like this. So the probability that x is greater than or equal to 4 is equal to 1 minus the probability x is less than or equal to, so greater than or equal to 4 is 1 minus the probability it's less than or equal to 3. Because every time you see the words at least, use the complement rule. Every time. So I'm finding the probability of the things I don't want, and then I'm going to subtract that off. So what is this going to look like? I'm going to put this in my calculator. 1 minus binom CDF 20.353. This is what I'm going to put in my calculator. Give you a second to write it down, then we'll do this. Okay, I'm going to pop over. I usually put the 1 minus in first, but it's okay if you just subtract it off after, because clearly we already have it right here. You could just subtract that off right now. I don't know if y'all know this, but you can copy and paste. Most of the calculators do this. Could do 1 minus, and then if I arrow up, I can highlight that and hit enter and it pastes it in. I don't know if your calculator does this, about most of them do. And I could just paste it in and then I could get my answer like that. Or 1 minus, I go into my second vars, go back to binom CDF. It's already in here. I have 20.353. I could paste that in there. So see, it says 1 minus this binom CDF stuff and hit enter. So just remember, every time you see the words at least, you are going to use the complement rule every single time. No exceptions. All right, so I'm going to go back to my other screen. So approximately 95.56% chance that if you took a random sample of 20, that at least 4 would have 3 or more cars. Questions? Okay. Let's jump to the next screen. All right, I would like you to try these. You might get stuck on D. You can just at least do A, B, and C. Go ahead and give these ones a shot. The first one is an exactly. The second one is fewer than or less than. And then the third one is at least. Give these a shot. If you get stuck, just sit there and look pretty until I can come back and help you. Till I go over it. I'm going to sit here quietly and let you do that, and then I'll work behind you. You're probably right, but I'm going to check myself. Yes, good job. Oh, good, good, good. I'm going to hold off on the last one so I can talk y'all through it. Give you a moment to finish up the third one. All right, how did we do? Any questions on the first three before I do the fourth one, or the fourth one? So be really careful with the fewer than, because a lot of times people will try to put the 3 in there, but because it's less than and not less than or equal to, be really careful with that. And the at least is where most people seem to struggle. So letter D, does anyone have an idea what we might do with letter D? All right, so I'm gonna drop.
Calculate 5 and 7 and then subtract 7 from 5 or subtract the 5 from the 7.
Yes, so close. We're gonna
Something
do
like
the 4 instead of the 5, but otherwise perfect because we want to subtract off the 4 because the 5 we want that. But otherwise that was perfect. So I'm just gonna put numbers here. Okay, I'm not going all the way to 20, but we want these. That's what we want. So what I can do is I can find the probability of 7 or fewer, and then I can subtract off the probability of 4 or fewer. So what this looks like is, whoa, that's not a pen. Hate when I do that. I can do binom CDF 20.417 minus binom CDF 20.414. And that's going to give me that center 5 through 7. You want me to show you guys what that looks like in the calculator, or are we? Yeah, okay. What was that?
Yeah, that'd be good.
Okay, I'm going to give you guys a second to write it down, and then I'll jump over to the calculator and show you what that's going to look like. All right, I'm going to pop over here and clear this because I don't like a messy screen. So I'm going to go into my vars here, my second. Uh-oh, I'm going to crazy places. Okay, so the first one I'm going to do is 20.41 and then 7. And I'm going to paste that. I'm going to put minus. That wasn't my minus button. Put minus, and I'm going to go back in. Second vars, and go back in. And do the same thing, but I'm going to put 4 in here. And it's not going to all show up on my screen, but you can kind of see. I'm going to scroll back. You can kind of see that it's all there. And then just hit enter, and it has done the subtraction for me. Yeah, good job. It is perfectly okay if you want to calculate them separately. If you want to calculate them separately, that's fine. If I wanted to, I could do is just delete this. Uh-oh, so I could do this instead. Some people aren't quite as comfortable putting a ton of stuff in their calculator all at once. And I just have been doing this a while, so I'm perfectly comfortable with it. I could do that. And actually, this is my favorite. I'm going to undo the second. I'm going to go up here and I'm going to copy this. So all I did is arrow up until it's highlighted. Hit enter. It pastes it, and I can go and change this to a 3 or a 4. Sorry, that's what I want. And then hit enter. Now, if I want to, I can go up here and highlight this and hit enter, minus, highlight, enter, bam. When I discovered the copy and paste, that was like a holiday. I should take that day off from work every year because it's such an important, cool thing. I'm sorry if yours doesn't do that. I think the TI-83 doesn't. Most of the TI-84s do, I believe. Questions? I'm going to pop back over here. Questions on this before we move on? All right, I'm going to move on. We're going to look at standard deviation and mean for the binomial probabilities. So our mean or our expected value, you just multiply the number of trials times the probability, and that's going to give you how many expected successes you can have. So if I know the probability of something happening, I know how many successes I can expect to happen. And then the standard deviation, which generally we use the standard deviation to find like outliers or to find if something is unusual. So it is the square root of the number of trials times the probability of success times the probability of failure. Okay, so sorry. Okay, so square root of the probability of success times the probability of failure times the number of trials, and that gives us our standard deviation. So we're gonna do a couple problems with this, and you can kind of see get an idea of how it works. Oh, wait, do you need this for a moment? Are we good? I feel another sneeze coming on. It's gonna happen. Okay. All right. So according to Experian Automotive, 35% of all car owning households have 3 or more cars. So in a simple random sample of 400 car owning households, we're going to get this mean and the standard deviation. So I want to know how many of those 400 would I expect? All right. How many would I expect to have 3 or more cars? So I just so my mu sub x is the sample size times the probability. It's really just that easy. I'm really not allergic to my cat. I don't know why I'm sneezing. Okay, so I would expect 140 people, 140 households out of that 400 to have 3 or more cars. That's what I would expect. That's what the expected value or the mean means here. I don't know why I have another sneeze coming on. Maybe. I don't know. All right. So now the standard deviation. So my standard deviation is sigma sub x. So I'm going to take the sample size times the probability of success times the probability of failure. So it's 1 minus 0.35. You're more than welcome to just put 0.65 in your calculator. I've just noticed in the past when I've just changed it to 0.65, I confuse people. So I quit doing that. So I just put it all in at the same time and just do second x squared, and then just do all of the math and it just stays under there nice and pretty. Your calculator might require you to put parentheses around the whole thing. So I have a standard deviation of 9.54. How'd we do? So the standard deviation, as usual, I would expect 95% of my samples to be within two standard deviations of 140. So I would, yeah. So the standard deviation continues to mean the same thing. Anything within two standard deviations of that mean would be considered normal. So if I had something, a sample that whose the number of car owning households is outside of that two standard deviation range, we would consider that unusual. Or anything with less than a 5% probability of happening, we would consider that unusual. Questions before we do another example? Or do it like a real example? All right. Okay. So this is a rule of thumb that we have with our binomial experiments, and we're going to use this rule for other things also, because a lot of times we don't use a lot of the math that we don't apply it to populations that are not bell-shaped. Things need to be bell-shaped or what we consider normal in order for us to do a lot of the math that we do in this class. And so the way that we test if something is normally distributed, which means it's bell-shaped, the way that we test is we do this math right here. If NP times 1 minus P is greater than or equal to 10, then we know that our distribution is bell-shaped. So we have to have a large enough sample size. We need a large enough sample size so that we get a good number of successes and failures. So that's because if I took a sample size of like 5, I'm not going to have very many successes and failures. My distribution of the sample that I take is not going to be normal. It's going to be really skewed one way or the other. It's too small of a sample size. As we do more and more trials, the more trials we do, our population is going to become more and more, or our binomial experiment becomes more and more bell-shaped. So the larger the sample size, the more likely we have a bell-shaped population. So we use this rule of thumb. And I think your next quiz has a question about this. So when you answer it, include this. Include this in your answer. When it asks you if how our pop or what happens as our trials get bigger, you can say it becomes more bell-shaped. Include this right here. Say as long as NP times 1 minus P is greater than or equal to 10, include that little tidbit with it. Because that's how we know that it's bell-shaped. We need to check that. All right. So according to the empirical rule, I kind of already said this, that if we have a bell-shaped distribution, which we just checked with this, if we have a bell-shaped distribution, then 95% of all of our observations are going to be within two standard deviations of the mean. Anything outside that interval occurs less than 5% of the time, therefore is considered unusual. So anything less than 5% of the time is unusual. I know we've already talked about this, but I'm going to keep on talking about it. It's not going to go away. All right. So This is the one that we just did. Except for, let's talk about this piece right here. We conducted a simple random sample, a researcher did, and found that 162 cars in his sample had 3 or more cars, or 162 households in his sample had 3 or more cars. We want to know if this is unusual. One of the ways you can do this is by doing your binom PDF and seeing if 162 cars is unusual. Or I can take a look and say, is 140 plus 2 times 9.54, is that going to be greater than 162? Is 162 going to be less than that or greater than that? I'm going to math that right now. This number right here, 159.08. Since 162, thank you, Gwen. Since 162 is not 162 is larger than 159.08, it would be an unusual result. It is outside of that 2 standard deviations. Therefore, it is unusual because this would be my upper boundary, right? So using the 2 standard deviation rule, it would be unusual to find 162 households have 3 or more cars. Questions? All right, let's do another one. So let's look back at the wireless only households. Let's go look at that numbers. I think it was 41%. I'm going to pop back here. It is 41%. I hate when they do that. So 41%. 41% of households are wireless only. We took a simple random sample of 300 households. We found 143 were wireless only. We want to know if this result is unusual. I'm going to give you a moment to find the mean, find the standard deviation, and determine if 143 is more than 2 standard deviations from the mean. I will work quietly behind you. I'm going to give you a head start though. That's exactly what I got, Gwen. Good job. Since 143 is larger than 140.04, it would be unusual to have a sample of 300 households where 143 were wireless only. I bet you that 41% is a lot lower than it is now. I'm guessing that the percent of houses that are wireless only is significantly higher than 143, but for this study and whenever it happened, this is what it is. Questions on this? This was our last slide. Have any questions? Okay, I'm going to leave you with the reminder. Every time you see the words at least, you will use the complement rule. Every single time without exception. Every time. I'm going to take the recording off and then you can ask questions off the recording in just a moment.